This is exponential growth and decay, part 1. Exponential growth occurs when a quantity increases by the same factor over an equal interval of time. The exponential growth function is represented by y equals a times the quantity 1 plus r to the t power, where a is greater than 0 and r is greater than 0. Exponential decay occurs when a quantity decreases by the same factor over an equal interval of time. The exponential decay function is represented by the form y equals a times the quantity 1 minus r to the t power, where a is greater than 0 and r is a number that lies between 0 and 1. Let's take a closer look at exponential growth. For exponential growth, the value inside of our parentheses, which is called our growth factor here, has to be greater than 1 because your r value is being added to 1, and since the r value has to be greater than 0, anything greater than 0 plus 1 is going to be greater than 1. Y represents the final amount that we end up with, while A is the initial amount, what we start with. And R represents our rate of growth in decimal form. So if something is growing by 20%, we would write that as 0.2. We always add it to 1. 1 represents 100%, which represents our initial amount. What we started with was 100%, and we're increasing it by a percentage. T represents our time. So let's say that the inaugural attendance of an annual music festival is 150,000 people. The attendance, which will be represented by Y, has increased by 8% each year. Write an exponential growth function that represents the attendance after T years, and then figure out how many people will attend the festival in the 5th year, rounding our answer to the nearest 1,000. So basically, when we're starting off, Y represents our final amount, A represents our initial amount, which the initial attendance was 150,000. That is increasing by 8% each year, so 0.08. So here is our exponential growth function. We can simplify it just a little bit by adding our 1 and our 0.08 to get 1.08. And now it really looks like an exponential function. So we have y equals a times b to the x power in that format. So how many people will attend the festival in the 5th year? Well, the first year we're going to count as year 0. That's the initial year. So the 5th year is actually going to be represented by the number 4. So the time will be 4. So I'm going to take my exponential growth function here, and in the place of t, I'm going to put in 4. So the first thing I would do is 1.08 to the 4th power, which is going to give me a very long number on my calculator. 1.36048896, and I'm going to multiply that by my 150,000. And remember, I'm being asked to round to the nearest thousandth, so I'm getting really an approximate answer. So I'll do my approximate sign here. Approximately 204,000 people will attend the festival during its 5th year. So we can use our function to make some estimates. And here we're estimating this will be the attendance in the 5th year. Let's take a closer look at exponential decay now. In exponential decay, the value inside of our parentheses, which we call our decay factor, is going to be less than 1. Because remember, r is a value between 0 and 1. And if we're taking that value and we're subtracting it from 1, we're going to get something less than 1. So once again, y is our final amount. A is what we start with. Here's the 100% we start with, and we're subtracting it by a rate of decay, which we put in decimal form. And t represents our time. So let's take a look at some of these tables and try to decide if they're showing us exponential growth, exponential decay, or maybe they're not exponential at all. So in this first table here, I notice that my x values are always increasing by 1, which is a good thing because that's a characteristic of an exponential function. It can also be a characteristic of a linear function though, so I have to look at my y values. My y values are decreasing each time I'm dividing by 3, or that could be multiplying by 1/3. So multiplying our y values is also a characteristic of an exponential function, but we notice they're decreasing here, so this is going to be exponential decay. All right, let's look at another example. So once again, my x values are going up by 1 each time. That's an exponential characteristic, but also a characteristic of other types of functions. I've got to look at my y values, and they are increasing. They're being multiplied by 2 each time. Multiplying our y values by a constant factor is an exponential characteristic. So once again, this is going to be exponential, but since our y values are increasing, this is going to be exponential growth. All right, the last thing we're going to do is take a look at some exponential functions and try to determine whether they represent exponential growth or exponential decay. And in these top two, we're also going to try to identify the percent rate of change. So this looks like an exponential function. If my value inside the parentheses is greater than 1, that's an indicator that this is exponential growth. If the value inside my parentheses is less than 1, and this looks like an exponential function, this represents exponential decay. But how do we find that percent rate of change? Well, I'm going to go back and I'm going to deconstruct these functions. I'm going to try to figure out how I got this 1.07 here. Remember, it's always 1 plus something or 1 minus something. So in this case, it's going to have to be plus. It's going to be 5 times 1 plus 0.07. So this 0.07 represents a 7% growth factor. In this case, we're going to have to be subtracting because we're getting less than 1. So we have to do 1 minus 0.02 to get our 0.98. So this decay factor here is 2%. Let's look at a couple trickier ones here. This time, this guy looks exponential, except our exponent is t divided by 4, which means we need to find the fourth root of 0.96. And I'm going to count on my calculator to help me with that. And I'm going to get a very long number when I do it. But I can basically just round, and it's going to be about 0.99, which is all I need to know, because if it's less than 1, this is exponential decay. Now in this guy, my power is t minus 3. When we subtract exponents, that's an indicator that we've been doing some division. So I'm going to rewrite this guy. 1.1 is my base. So I'm going to do t for the top exponent, 3 for the bottom. So t minus 3 would be a way to simplify this. I'm working backwards. So I can do on a calculator 1.1 to the third power. That gives me 1.331. And on the top, I've still got my 1.1 to the t power, which I can't do because I don't know what t is here. I can add my ghost 1 here, my factor that I'm multiplying by, and I can do 1 divided by 1.331, which simplifies to approximately 0.75 and parentheses 1.1 to the t power, which is really all I need to know, because once I see that I have 1.1 in my parentheses and it's greater than 1, I know this is going to be exponential growth.